Welcome to today's paper reading. Today's paper is titled, Temporal Residual Guided Diffusion Framework for Event-Driven Video Reconstruction. This paper was published on AR14 by Lizhi and colleagues from Beijing Institute of Technology. Event-based video reconstruction is gaining attention due to its high dynamic range and rapid motion capture capabilities. However, current methods often overemphasize low-frequency texture features, leading to over-smoothing and blurry artifacts. To address this, we introduced the Temporal Residual Guided Diffusion Framework, which integrates temporal features, low-frequency texture, and high-frequency events to guide the Denoising Diffusion Probabilistic Model, DDPM. Our framework includes 3 key conditioning modules and uses a temporal domain residual image to capture scene variations. This approach effectively reconstructs high-quality videos from event flow, outperforming previous methods in mitigating artifacts and over-smoothing issues. Event cameras offer unique advantages such as high dynamic range and the ability to capture rapid motion. However, existing methods for event-based video reconstruction often focus too much on temporal information, leading to issues like over-smoothing and loss of high-frequency details. Diffusion probabilistic models have shown promise in image generation, but integrating degraded images and conditional information remains a challenge. This paper aims to address these issues by introducing a novel framework that strategically incorporates both temporal and high-frequency event priors. Figure 1 illustrates the common issue in existing event-based reconstruction methods where an overemphasis on low-frequency texture leads to over-smoothing and the loss of high-frequency details. This issue motivated the development of a framework that strategically incorporates both temporal and high-frequency event priors to improve image reconstruction quality. The figure highlights the contrast between the frequency domain components of the scene and the reconstruction results, emphasizing the need for a balanced approach that captures both low and high-frequency information. Early approaches in event-based video reconstruction focused on the similarity between events and gradients, or the use of optical flow to directly reconstruct scene structure. However, these methods struggled with achieving realistic intensity images due to a lack of long-term data exploration. With the advent of deep learning, methods like E2VID, FireNet, and sparse E2VID have shown significant improvements. E2VID uses LSTM and optical flow constraints on large datasets. FireNet achieves faster reconstruction speeds with a lighter architecture, and sparse E2VID emphasizes high frequency by learning gradients. Despite these advancements, challenges remain in balancing long-term and short-term event features, leading to motion artifacts and blur in reconstructed images. The application of diffusion models to image and video restoration tasks has gained popularity following the success of DDPM in generating images from random noise. Methods like SR3 and PLAT use degraded images as conditions, while shadow diffusion and IDM utilize pre-processing features. Efforts to improve efficiency include ReStiff and UCTR, which employ additional pre-processing models, and IRSD and Refusion, which altered the diffusion process to start from noisy degraded images. Refusion and DiffIR encode images into a latent space for faster processing. Additionally, low-cost restoration methods like SNPs and DDRM perform decomposition using well-known degradation models, and DPS and GDP guide the sampling process based on Bayesian theory. Event diffusion applies diffusion models to event-based image reconstruction. In event-based reconstruction, events are represented by their pixel positions, 11, E timestamps, TI, and polarities, pi. The polarity indicates the relationship between scene brightness and time variation. The Temporal Residual Guided Diffusion Framework transforms events into two-dimensional images and segments them based on event density to estimate the scene video. Frequency domain analysis is performed to compare different methods, focusing on the reconstruction of high-frequency details and susceptibility to noise interference. Figure 2 compares different strategies for event-based reconstruction. Strategy A directly predicts intensity images from the accumulation features of past events, exemplified by methods like E2VID and ETNet. Strategy B involves joint reconstruction from event feature accumulations and predictions from the previous frame, as seen in SPADE E2VID. Our proposed strategy, C. Uses a temporal residual guided diffusion framework, which addresses the loss of high-frequency information by generating high-frequency temporal residuals through a conditional diffusion model. This approach effectively balances the extraction of temporal features with the preservation of high-frequency details, leading to more realistic reconstruction results. Figure 3 presents a frequency domain analysis of reconstructed results. It includes the original image, A, the Fourier spectrum chart of the intensity image, B, and the high-frequency components of the intensity image, C. A local magnification diagram, D, is also provided for scaled representation. The analysis reveals that despite the similarity between events and the high-frequency map of the scene, methods like E2VID and ETNet fail to reconstruct precise high-frequency details, resulting in blurred edges and increased noise interference. In contrast, the high-frequency components of the results from the described method closely match the event's voxel, indicating effective utilization of high-frequency features of events at the current time. Figure 4 provides an overview of the temporal residual diffusion framework. In stage I, a pre-trained intensity predictor is employed to generate an initial low-frequency estimation. This estimation serves as a foundational step for the subsequent stages. Moving to stage 2, the residual image is computed in the time domain, and Gaussian noise is added to this residual image. This step is crucial for the diffusion process, which aims to model the distribution of the data. Finally, in stage 3, a triple-path conditional model is utilized to predict the noise added in stage 2. This model leverages the temporal information and the residual image to refine the noise prediction, thereby enhancing the overall accuracy and effectiveness of the diffusion framework. Figure 5 provides an overview of two key components in the temporal residual diffusion framework. Part A illustrates the process of sampling a video, where the conditional diffusion model integrates current events, intensity estimation, and features from accumulated events in the previous moment to guide the generation of high-frequency temporal residuals. These residuals are crucial for enhancing the intensity image of each frame. Part B details the architecture of the res block with cross-attention, which emphasizes the integration of events accumulation and intensity estimation features on noisy temporal residuals, facilitated by group normalization, GN. This dual focus ensures the model's ability to accurately predict and refine the intensity images, contributing to the overall quality of the generated video. In evaluating the temporal residual guided diffusion framework, the authors utilized the COCO dataset with the ESIM simulator for training. For testing generalization performance on real-world events, multiple real datasets were employed, including IJRR, HUF, and MVCC. The iteration number T was set to 2000 during both training and testing phases. The proposed method was compared against various state-of-the-art event-based reconstruction methods such as E2VID, E2VID+, FireNet, FireNet+, SPADE E2VID, and ETNet. The evaluation metrics included mean square error, MSE, structural similarity, SSIM, and perceptual loss, PIPS. All reconstructed images and APS reference frames underwent histogram equalization before evaluation to ensure fairness. The results demonstrated state-of-the-art performance across almost all metrics, with significant improvements in structural details and SSIM metrics. Figure 6 presents a qualitative comparison of our method against others on the HUF, IJRR, and MVCC datasets. Our results demonstrate the closest brightness distribution to the APS reference frame and the sharpest texture details. This visual comparison highlights the superior performance of our approach in maintaining brightness accuracy and detail sharpness, which are critical for effective event-based reconstruction. Figure 7 presents a detailed comparison of different event temporal accumulation methods. Subplot A visually contrasts scenarios with and without event accumulation, highlighting the differences in image reconstruction quality. Subplot B provides quantitative results across multiple metrics over time, showing how different accumulation strategies affect performance. The figure demonstrates that event accumulation significantly impacts image brightness and contrast, with continuous accumulation leading to more balanced and detailed reconstructions. The absence of accumulation at certain time steps results in sudden drops in quality, emphasizing the importance of consistent event processing. Figure 8 presents a visual comparison of ablation experiments, highlighting key variations in the diffusion model's approach. The second column, labeled No Residual, shows the model generating the target intensity image directly without using temporal residuals. The third column, No Event, demonstrates the model's performance when guided solely by initial intensity estimation. The fourth column, No Cross ATT, illustrates the impact of removing cross-encoder attention mechanisms during the encoding phase. Finally, the fifth column, All, showcases the results of the final model incorporating all features. Figure 9 illustrates the impact of different inference steps on multiple datasets. The results show that as the number of inference steps increases, the performance metrics such as SSIM and LPIPS improve significantly. This improvement is particularly notable in datasets where the noise step size is larger. The mean squared error, MSE, metric, which focuses on brightness differences, converges rapidly compared to other metrics. Overall, the metrics tend to converge when the number of iterations exceeds 1,000, indicating a stable and optimal performance level for the model. Table 1 presents a quantitative evaluation of various methods on multiple real datasets, highlighting the best results in bold. The evaluation metrics include mean square error, MSE, structural similarity index, SSIM, and learned perceptual image patch similarity, LPIPS. The methods compared are E2VID, FireNet, SPADE E2VID, and others. The table shows the performance of each method across different datasets, with the best results marked in bold. Table 2 presents a quantitative comparison of various strategies used in the study. The table highlights the performance metrics of mean squared error, MSE, structural similarity index, SSIM, and learned perceptual image patch similarity, LPIPS, for different combinations of strategies including residual, recurrent, cross-attention, and event-based conditional diffusion. The best results are marked in bold, showing the effectiveness of each strategy in improving the reconstruction quality. For instance, the strategy with all components included achieves the lowest MSE of 0.0707, the highest SSIM of 0.2768, and the lowest LPIPS of 0.2892, indicating superior performance in terms of accuracy, structural similarity, and perceptual similarity, respectively. The Temporal Residual Guided Diffusion Framework addresses the challenges of event-based video reconstruction by effectively integrating temporal features, low-frequency texture, and high-frequency event features. This approach significantly enhances the Denoising Diffusion Probabilistic Model through 3 key conditioning modules, ensuring more accurate and artifact-free reconstructions. By leveraging temporal domain residual features, our model captures both temporal and high-frequency event information, outperforming previous methods in extensive benchmark experiments. This marks a significant advancement in achieving high-quality event-based video reconstruction. Thank you for watching.